covered. Good morning, everybody. We start the week covering fusion systems, having covered in some detail fission systems. And fusion is considered a future source of energy that is basically almost so large in size that it can be considered as a permanent source of energy for a civilization trying to reach the level 1 civilization according to the Kardashev scale. So along this line, we switch and shares the screen, and sharing the screen, in that case, we find our way to the part of the course that deals with fusion systems here. We haven't covered any of those chapters yet, and we have time, really, in fact, to cover all of them. Let's talk about plasmas in general, because fusion is covered through is part of the process of nuclear reactions where the nuclei are combined together. Fusion and fission, of course, are terminologies from the biological field where cells can combine or fuse together. It's interesting to observe that fusion is the basic source of energy in our universe, and it is the main source of energy in our star, the sun. We know that hydrogen in our star, the sun, is fusing, turning into helium as a product of the fusion process, with the help of several catalysts, so to say. It is interesting to know that catalysts can include other isotopes like carbon and nitrogen in that case. You could see here the heliosphere, which, or the corona here of the sun, the corona of the sun, where some prominences here along magnetic field lines show us the emission of charged particles from the surface of the sun. So fusion can be considered as the mother of all energies, where in that case, not the fission of the nuclei is the source of the difference in mass in Einstein's equation that gives us the energy, but it is the fusion of the nuclei. When the helium nuclei fuse together, in that case, they end up with, when hydrogen nuclei fuse into helium, there is a difference in mass that is, of course, initially kinetic energy, and then it becomes heat energies in general. It's very interesting that fusion research is proceeding in leaps and bounds. For 30 or 50 years now, people have been trying to reach a fusion device that is self-controlled. We know that we release energy in thermonuclear reactions. In that case, the two isotopes of hydrogen, deuterium and tritium, are fused together in what we call thermonuclear weapons or thermonuclear devices, or hydrogen bombs, in fact. And we know that in that case, the release of energy is not in a controlled fashion. Since the Earth is a water planet, we have tremendously large supplies of deuterium in our oceans. And deuterium plus deuterium is a reaction that can produce also fusion energy. Thermonuclear research have been proceeding. There are, as we'll see later, significant progress lately. There is a progress, for instance, in maintaining a long enough self-sustained chain reaction at a laboratory in the UK, Coulomb laboratory. But many people are some kind of interested, and it is a goal of scientists to reach a controlled, not an uncontrolled fusion reactions. That started with many different devices. So I quote here a quote by Mr. Alfvén. He's a Swedish Nobel Prize laureate. Quote, since thermonuclear research started with Zeta, Tokamaks, Stellarators, we'll cover the Tokamaks and Stellarators as possible devices to produce fusion energy. Not to forget one that is funny named, perhaps Atron. Plasma theories have absorbed a large part of the energies of the best physicists of our time. The progress which has been achieved is much less than was originally expected. The reason may be from the point of view of the traditional theoretical physicist, a plasma looks immensely complicated, and that is true. We may express this by saying that when by an immense numbers of vectors and tensors and integral equations, theoreticians have prescribed what a plasma must do, the plasma is so silly that it does not understand the sophisticated mathematics, or it is that the plasma is so clever that it finds other ways of behaving, ways which the theoreticians were not clever enough to anticipate. Perhaps the noise generation is one of the nasty tricks the plasma uses in its IQ, intelligence quotient, competition with the theoretical physicists. So Alfvén here was being obviously funny, but that is an interesting description of fusion, is that the theory does not match the practice. So if you want really a controlled fusion reaction, you have to build devices and achieve it experimentally. What is the word plasma? Plasma was introduced in 1928 by the famous scientist Langmuir in a paper titled Oscillations in Ionized Gases. So the physics of plasma are part of the physics of ionized gas in general. He does not give a motivation for using the word, but it has been adopted as a state of matter where the gas, in that case, is ionized, meaning that the electrons are stripped out of the atoms, leaving ion, hence the word ionize. In his introduction, Langmuir is quoted, we shall use the name plasma to describe this region containing balanced charges of ions and electrons. A plasma is always surrounded by what is called a double layer. It tries to protect itself from the environment by that double layer or a plasma sheath, in the same way that a cell in our body is also protected by a wall of the cell itself, in the same way that any biological cell protects itself with a cell well from by its environment. Almost all matter in the universe can be described as a plasma, starting from the phenomenon of the plasma of occurring in our star, the sun. This shows here some prominences of magnetic fields. The magnetic field of the sun acts like rubber bands, and we know that charged particles rotate around the magnetic field lines. So that's the surface of the sun. We see a prominence here of charged particles being ejected from the surface. The same phenomenon happened on Earth here in the process of lightning discharges. We get a plasma in that case. The heat generated in a lightning discharge is so high that it ionizes the air, and the electrical discharge follows the ionized line. In fact, the interesting thing is that it's not shown in that picture, but the lightning strike starts from the top of the clouds to the earth, and then there is a leading edge. Another lightning bolt starts from the earth and meets, the two of them meet at a certain height. The aim of scientific research in plasmas is to try to imitate what happens in nature in our stars, and this is a fusion plasma that's laboratory produced on Earth, and basically this is probably an inertial confinement type of a device, but this is the goal of the research in plasma and fusion, to imitate what happens in nature and control the release of energy from a plasma in general. We did mention that we have learned about plasmas quite a bit by studying the solar wind. And the solar wind, of course, is that those discharges from the sun to our Earth in the form of electrons as well as protons. And we call it the solar wind. It is intercepted by the Earth's magnetic field. In the northern hemisphere, those charged particles are trapped in the magnetic field and then find their way to the Earth in what's called the Aurora Borealis, or the northern lights. In the southern hemisphere, those charged particles from the sun are displayed in the form of the Aurora Australis, and that is what we call the southern lights. Most of the universe, as I suggested, is in the form of plasmas. Some people even suggest a plasma model of the universe in competition with models of gravitational energy and so on. But there are different forms of plasmas that are described according to the temperature in kelvins and the densities. So let's compare them. The solar corona that we described earlier has 1 million particles per centimeter cube. So it's quite a dense, a slightly dense plasma. But interstellar gas, you find that you have 1 ion per centimeter cube. So that is the N is the number of particles. The ionosphere around the Earth, this is an area that is ionized and it reflects radio waves, is also the same as a solar corona at 1 million particles per centimeter cube. The temperature is different though. See here, the solar corona has a temperature of 1 million Kelvin, quite hot there. The ionosphere is only 1,000 kelvins in temperature. Laboratory plasmas could be Q plasmas, and that's 100 million particle per centimeter cube. The dense Q plasma 10 to the 11th, a tenuous hot plasma 10 to the 12th. And we are familiar with arc discharges in the welding of metals. You find that you generate a plasma, but the density there is quite high, 10 to the 14th particles per centimeter cube. Dense hot plasmas in laboratories are 10 to the 16th, and thermonuclear plasmas that we try in our, of course, that are used in thermonuclear devices or hydrogen bombs are 10 to the 16th, and that's the same that is used in laboratories trying to initiate a self-controlled plasma in general. Here is a picture of what I mentioned, that the Aurora Borealis, which is a solar wind intercepted by our magnetic field on Earth. This is the northern light, not so far from us. It's really, if you travel over the summer to Traverse City in Michigan, a wonderful place to visit. If there is solar activity, you could see the northern lights here as beautiful curtains of light where the electrons and the protons interact with the nitrogen and oxygen in our atmosphere. And that description as curtains of light is really nice because you'll find those things moving around, and basically it's all kinds of light and X-ray excitation of the nuclei in the atmosphere. This is close to us here. When the sun is active, you find that those northern lights can be seen at lower latitude in the United States. But in Norway, that's a common occurrence, Norway being close to the North Pole, the magnetic North Pole of the Earth. And this is a view of those northern lights. The description of how the Earth intercepts the solar wind has been discovered by satellites. Explorer 1 satellite, for instance, had the cosmic radiation detectors on board, and it discovered 2 zones of radiation from the sun that are intercepted by the Earth's magnetic field. And if this is the North magnetic pole here, the South magnetic pole here, you'll find that we have definitely two regions shown here, this little closed region and another outer region where the particles from the solar wind are intercepted and trapped in the Earth's magnetic field. And we wrote earlier the Lorentz equation, or what the French call the Joules equation, that describes the behavior of a particle in an electromagnetic field. If it's an electric field, you'll find that charged particles move in the direction of the electric field. But in the case of a magnetic field, the particles rotate around the magnetic field lines. So if the rotation of the Earth creates a magnetic field, you'll find that those particles now rotated around the magnetic field lines from the North Pole to the South Pole, and some of them get trapped at those heights. Evidently, it's these Van Allen belts, as they're called, are of great interest for our engineers, electrical engineers, designing and launching satellites for communications, or GPS, the GPS system too. So they're positioned out of those radiation belts, because that radiation there, the charged particles that can affect the electronics. Any spaceship, of course, instrumentation has to be protected, or the terminology is to be hardened, the electronics against the possible damage by the radiation from the electronic belt, and they're positioned outside the radiation belts. It is also known in that case that the International Space Station is positioned outside the radiation belts in synchronous orbit satellites in general. A depiction of these magnetic field regions is shown here. The Earth would be in the center. The Earth's magnetic field lines are evolving from the North Pole to the South Pole. And you could see that here the inner Van Allen belt, and this would be the outer Van Allen belt. Any satellites that are launched out of the Earth have to go through those two belts before they're placed in geosynchronous orbit outside the radiation belt. What is the altitude in that case? The International Space Station is positioned at 240 miles above the Earth. The inner Van Allen belt is an altitude of 1,000 to 8,000 miles, and the outer Van Allen belt is 12,000. In that case, 25,000 miles, and this orbit here at the very far end of the outer Van Allen belt is what we have, the orbit of geosynchronous satellites, 22,000 miles. So in that case, the orbits of the particles rotating around the magnetic field lines from the North Pole to the South Pole and vice versa are called the banana orbits in that case, because they rotate around the magnetic field lines from the North Pole to the South Pole, rotating, and then here the magnetic field lines come in very close to each other, and the velocity vector of the charged particles is reversed, so they simply change direction and go back in the opposite direction. So they go back and forth between the North Pole and the South Pole. Now, why are we studying this? Because this is the situation that humans are going to be trying to develop or use in trapping charged particles in a magnetic field, and we call this magnetic confinement as a way of achieving a self-controlled chain reaction in terms of fusion in general. Notice that the International Space Station is positioned at a height of 240 miles, way below the altitude of the inner Van Allen belt at 1,000 to 8,000 miles. Some interesting trivia here is that when you hold the compass in your hand, the north pole of the compass basically points to the north of the Earth, but it is in fact pointing to the south pole of the Earth. So the terminology is reversed, since in a magnet, the opposite poles attract. So the north pole of your compass is pointing to literally the south pole of the Earth, the south magnetic pole of the Earth. So again, here you find that we are trying through particularly the two devices that we are going to explore, the Tokamak and the Stellarator, or the tandem mirror, as ways of imitating the trapping of those charged particles in the Earth's magnetic field. We did mention earlier that without the protection by the Earth's magnetic field, the surface of the Earth, the water, the Earth being a water planet, would have been evaporated to outer space, and the Earth would be with a very thin atmosphere, like the atmosphere of Mars, and the Earth would be a dead planet. We know that the magnetic field of the Earth is caused by the rotation of the outer core of the Earth, which is metallic in iron and nickel, containing lots of electrons. So it's a dynamo protecting the Earth from too much of a good thing, the solar wind. This describes to us this idea of the banana orbit, where the charged particles rotate around the magnetic field line. When they bunch together towards the South Pole, they reverse direction. They go back to the North Pole and come back to the South Pole. And that North Pole and South Pole basically projects themselves in a circular fashion, not this diagram, but more like a circular fashion at the North Pole and South Pole. And that is exhibited in the northern and southern lights, the Aurora Borealis and the Aurora Australis. A nice depiction of what the situation is shown here. This would be the Earth here, a belt that's an inner belt at about 1,000 kilometers in the form of a torus surrounding the Earth. Then you have the outer belt at 12,000 miles here, and you have the inner belt. Let's see, the inner belt is at 1,000, 8,000 miles. The GPS, or the geographical positioning system satellites, are positioned in between that very small inner belt and the larger outer belt at about 12,500 miles, because if you would position them within the radiation belts, then the instrumentation would be ruined. You have to be careful to harden the or shield the instrumentation and the electronics so that they don't get affected by the charged particles in the radiation belts. Those radiation belts can change their position when we get solar flares or solar phenomena, where the density of the trapped particles becomes larger than under normal conditions. The positioning of the GPS satellites, as I suggested, 12,500 miles in between that inner belt and the outer, larger outer belts. And and the synchronous orbit, the Solar Dynamic Observatory, for instance, is positioned on the outside of the radiation belt. So we position our satellites or the International Space Station in regions around the Earth where the intensity of the Van Allen belts is low. How low is it low? In the inner zone, around a height of 2,200 kilometers, you'll find that the trapped particles are electrons and protons. So this is ionized particle, so it's a plasma in that case. The threshold energy of those particles are in the range of about 600 kilo electron volt of energy, and the intensity is about 10 million particles per centimeter squared per second per steradian. Steradian is a unit of the solid angle in that case. In the outer zone, at 16,000 kilometers, an altitude of 12,000 to 1,900 kilometers, again, it's electrons and protons with energies in the range of 20 to 200 kilo electron volt and an intensity of 1 billion particles per centimeter squared per second as intensity or flux. Some people designate it as flux. Okay, now particles that charged particles interact with the magnetic field by rotating around the magnetic field lines. However, the process of fusion itself depends on, since now we have ions of the hydrogen that we want to fuse together, and now you have a barrier that prevents particles to fuse or to combine with the nucleus of the atom, and we call this the Coulomb barrier. So it's a repulsion, electrostatic repulsion, shown in a diagram right here. If you have a nucleus, the positive charge repels any incoming charged particles, and the charged particle has to overcome that Coulomb barrier that depends over 1 over r squared, the inverse square law, to be able to combine with the nucleus. If you want to show it as in a 2 dimensions here, that 3-dimensional Coulomb barrier becomes like a well that represents the center of the nucleus, and your charged particles have to climb that hill and to be able to fall into the nucleus and combine with the nucleus. So that means that its kinetic energy must exceed the level of the Coulomb barrier. And that means that we have to study what is that Coulomb barrier that we have to surmount to have a charged particles coming in this direction be absorbed by the nucleus of the target nucleus. Well, that would mean that the particle must have a very high energy equal to the electrostatic propulsion of the nucleus. If it doesn't have enough kinetic energy, you'll find that the charged particle will come in here close to the Coulomb barrier and get deflected away, or it can be reflected back, and it needs to go up to the Coulomb barrier. We'll show here some numbers very soon, in that energy could be quite large. In that case, all the charged particles would come, the charged particles like nuclei of hydrogen would come close to each other, but do not fuse together. But we are fortunate enough in nature in that those particles having high energies behave like waves. And a process that's very interesting is that they can penetrate that Coulomb barrier through a process called tunneling. So in that case, we still can have charged particles with low energy penetrate into the nucleus of the atom and cause a process of fusion. So the Coulomb barrier, yes, you need high energy to go over the top here. Let's think about it as a volcano. But the process of tunneling also occurs, and that's what we depend on in achieving fusion energy on Earth in general. All right, so let us become quantitative here and study the problem of how to cause 2 nuclei to fuse together, to join into each other. Maybe a deuteron to fuse with another deuteron, producing other charged particles that we balanced as equations before. We called it the Dd reaction, or a deuteron and a triton, we called it the Dt reaction. So let us consider a nucleus, and we know that the radius of the nucleus is proportional to the mass number of the nucleus to the 1/3 power. That 1/3 power here gives you some implication that it has to do with the volume of the nucleus. So that number will be small for the small nuclides like hydrogen, deuterium, and tritium, but quite large for uranium and thorium. We don't talk about the fusion of two thorium or two uranium nuclei, but we talk about the fusion of two deuterons or a deuteron and the triton nuclei. So you find that R is 2.5 10 to the minus 13, A to the 1/3 power in centimeter. So if your A here is 1 hydrogen, you'll find that the radius of the nucleus is in the range of 2.5 10 to the minus 13 centimeter. You could see that's a very, very small radius. If you say 10 to the minus 12, and you say that the atom size practically is 10 to the minus 8 or 1 angstrom, you'll find that there is a factor of 10,000 between 10 to the minus 12 and 10 to the minus 8. And you can get an analogy here is that if you have a football field, the football would be the nucleus and the atom is the size of the whole football field, 10,000 times the size of the football itself. So that's just to get an idea about how around us we have basically vacuum, but what we perceive is the interaction of lights and X-rays and so on with in the material world. All right, so if you take the diameter then of the nucleus and test to the minus 13 centimeter, and if we consider the Coulomb repulsion, we know in the CGS system of units, since we are using centimeters here, the force, the Coulomb force in dynes, that's a unit of force in the CGS, centimeter, gram, second system of units, is the charge of the nucleus multiplied into the charge of the incoming particle divided into R squared. So the inverse square law applies in that case. Z1 and Z2 would be the atomic number of the two nuclei that we are trying to get to fuse together. And you could see here that they are repulsed from each other with a force, which we call, of course, a Coulomb force in that case. The charge of the electron here, this is the total charge of the nucleus, E is the charge of the electron. In the CGS system of units is measured in stat coulombs or electrostatic units. The charge is 4.8 10 to the minus 10. And if the two nuclei collide head on with enough kinetic energy, they can get close enough for the short range nuclear force to overcome the potential energy due to the Coulomb repulsion. The potential energy due to the Coulomb production replaces that R here now, R squared, that replaces the R squared with R, and we can estimate really the energy in units of ergs that the two nuclei of charge Z1e and Z12 have to overcome when they come close to each other. They come close to each other when the radius of the first nucleus plus the radius of the second nucleus are touching each other. And if you plug in some numbers, assuming that R1 is equal to R2, then you end up with that energy in ergs that overcomes the Coulomb energy is Z1, Z2, E squared divided in twice R, assuming that, say, we have two deuterons maybe trying to fuse, and we are trying to fuse them with each other. We have written an expression for the radius of the nucleus as A in terms of the mass number A to the 1/3 power. And here we had the constant 5 10 to the minus 13. So you'll find that we can write an expression for the energy in ergs, the unit of energy in the CGS system of units, as Z1, Z2 divided into A, the mass number to the 3rd power. Just to get a better idea in a different system of units, this is in ergs. We know that 1 million electron volt is 1.6 10 to the minus 6 ergs. So we can convert that energy into million electron volt by that conversion factor, and we get that E, the repulsion energy, is 0.288 Z1 Z2 over A to the 1/3 power. And from there, we can estimate what is the minimum energy that we need for us to overcome, to be able to get two nuclei to combine with each other. So what happens is the sun or all the stars, this is the mother of all energies, is really that hydrogen nuclei fuse together, and they have to overcome in the stars that Coulomb energy. The minimum amount would be if we have hydrogen, so Z1 and Z2 are equal to 1, and the mass number is 1. It makes the calculation very easy. So the minimum energy, according to classical theories, this is not quantum theory. Quantum theory would consider the nuclei not as particles, but more like waves, is 0.288 million electron volt. So this is the minimum amount of energy that we have to give two particles in a star like the sun to overcome the Coulomb energy repulsion. However, because of increased electrostatic propulsion, we actually in practice need larger energy would be required to overcome the Coulomb barrier for having a higher atomic number nuclei. When A becomes larger here, this is a small number, the denominator, you find that E becomes much larger. So, but this tells us something interesting, that equation that we derived here, that if we have Z1 and Z2 as light nuclei like deuterium and tritium, the overcoming of the Coulomb barrier and causing fusion would become easier than using, say, uranium or thorium or even iron or calcium in the middle of the periodic table. So in fact, when we talk about fusion, we talk about light nuclei because of the need to overcome that Coulomb repulsion. As I suggested, luckily for us, experiments with accelerated nuclei have shown that nuclear reaction can occur at energies far below that energy that's required by the last equation that we derive, which is the Coulomb energy. And that underlies the quantum mechanical process of that fusion process. The nuclei acts like waves and can go through the Coulomb barrier through almost like going through a tunnel. And we call this a tunneling effect, rather jump above the barrier like the model of the volcano that we have shown earlier. The fact that tunneling exists allows us to attain fusion energies not in the million electron volt regions of the interacting particles that we derived here, but in fact in the 10 kilo electron volt for deuterium and tritium fusion, deuterons fusing with tritium, and the 100 kilo electron volt for deuterium and deuterium, as we'll see. So it's a factor of 100 less coming to us through the tunneling effect in general. All right, again, learning about fusion in general in our universe suggests that we can learn more about how to achieve self-controlled fusion on Earth. The fusion reactions converting hydrogen to helium occur in the stars in general, and we need to learn about how fusion occurs in the stars as a way of getting inspiration on how to achieve it on Earth. You'll find that the central temperatures in those stars can reach basically 20 million Kelvin, very high temperature. Temperatures means what? Means that those nuclei are moving with very high energies, interacting, colliding with each other, overcoming the Coulomb barrier through tunneling or through even overcoming the barrier itself. And this is how fusion reactions occur in the stars. And the stars, as we know, have primarily hydrogen. So those hydrogen or proton in that case, because now we call it a proton, if the hydrogen atom is stripped of its electron, it's an ion, and it's literally a proton. And this was discovered by prominent scientists Hans Bethe and Critchfield in 1938, and other people like Lauriston and William Fowler developed it further in general. The proton-proton chain has a peculiarity is that a proton can combine with a proton, and then the proton plus proton can reverse the reaction in general. And occasionally a proton also turns into a neutron and a positron. And in the case of the generation of the positron, we know that for conservation of parity and momentum, a neutrino would be emitted. So we call that neutrino here. This is a nu, or N in the Greek alphabet. Nu sub E is an electron neutrino. The neutron and the proton can stick together also as a deuteron. And the nucleosynthesis, as we call it, of helium in the stars, hydrogen turning into helium, can also occur with a nucleus of helium-3 combining or fusing with a nucleus of helium-3, generating eventually the helium that we know is the end product of the hydrogen reactions in our stars, with 2 hydrogen also emitted. Another reaction that can be considered, we know now how to balance the nuclear reactions, is a helium-3 plus a helium-4 turning into beryllium-7. The relative occurrence of this main reaction is known from experimental data. So the scientists got information about the reaction that happened in the stars by experiments in particle accelerators in general. The main reaction that happens in that proton-proton chain consists of 3 reactions, and we have seen how to balance those reactions. 2 hydrogens combine with 2 hydrogen, producing a deuteron, which is a heavy isotope of hydrogen. A positron emitted, 2 neutrinos are emitted. When a positron here, a positive electron is emitted, a neutrino is emitted, and you find that you release 2.38 million electron volts of energy, which is really because the balancing took 2 here, 2, 2, 2, 2, then it's 2 times, if you have only 1 hydrogen plus 1 hydrogen, 1.19 million electron volt of energy. All right, so in that case, what happens is that deuteron now has high energy. It meets another hydrogen nucleus at high energy, produces helium-3, 2 gamma photons are emitted, and 11 million electron volts of energy are released. Now, what happens is that helium-3 finds another helium-3 nucleus, forms a helium-4, and the proton is emitted. These are 3 chain reactions here that you can add together. And you notice when you add them, deuterium and deuterium here disappear from the overall reaction. It is acting as a catalyst. The same way for the helium-3, it acts as a catalyst. So the end result, you find that the deuterium here and the helium-3 disappears from the left-hand side. We are left with 2 hydrogen atoms cancel with 2 hydrogen atoms. So we are left with 4 hydrogen atoms, or nuclei in that case, to be more exact, in that proton-proton chain reaction produces helium-4, 2 positrons, 2 neutrinos, and 2 gamma photons, and a very large amount of energy, 26 million electron volts are released. This is the proton-proton chain reaction. And in that case, as I suggested, deuterium and helium-3 are catalysts for the reaction. Catalyst is a definition in chemistry of isotopes or the elements that take part in the reaction, in the detail of the reaction, but in the end products, they simply do not appear. So in that case, these are nuclear catalysts rather than chemical catalysis in general. Now, that proton-proton chain is the base reaction that happens in stars in general, where we said that the most common element in the universe is the protons or the hydrogen nuclei, and stars in general have their hydrogen turning into helium-4 with all those other products being generated, gamma radiation, positrons that find an electron and then turn into gamma photons again. And the neutrinos are also emitted to balance the momentum and the parity of the reaction. The helium-3 nucleus can interact in a different way, leading to different branches. So in that case, it's shown here. I'm not going to go through the detail. A proton plus a proton gives it deuteron. Deuterons interacts with the hydrogen, gives helium-3, but the helium-3 can interact with helium-4, generates beryllium-7. The beryllium-7 finds a negative electron, turns into lithium-7. The lithium-7 combines with the hydrogen, leading to 2 helium-4 nuclei. The end result of those equations is the same as the first equation. Is that 4 hydrogen nuclei plus a negative electron generate a helium in general. So our star, the sun, is in fact undergoing that reaction where whether it is the main branch here of the proton-proton chain, 4 hydrogen nuclei giving us helium-4, or 4 hydrogen atoms interact with a negative electron giving us helium-4. Another branch here in the last branch, the beryllium-7 can interact differently. So we get another set of chain reactions. If we add all those reactions and cancel the catalysts from both sides, again, we get 4 hydrogen nuclei giving us helium, 2 positrons, 2 neutrinos, and 3 gamma photons, and an energy release of 19 million electron volts is achieved. So in the main branch, 2% of the energy is carried out by neutrinos. And the idea of neutrinos, the solar neutrinos, has been a challenge for astrophysicists for a long time. At some point, they were thought not to be particles that didn't have enough mass. They penetrated the whole thickness of the Earth from one side to the other without interaction. And we have a chapter on neutrinos as particles that you can access by itself. 4% the value in the first branch. In the second branch is much larger. It's 29%. Early biological life on Earth and the fossil, solar, and wind energy supplies are dependent on this fusion nuclear reaction. So you notice that the source of all energy on Earth, including the renewables here that we consider as wind and solar and geothermal, maybe because that's, well, geothermal is more like radioactivity, but the fossil, solar, and wind energy supplies, fossil, of course, being all dead plant and animals that were generated through photosynthesis, through that's from solar radiation. So most of our energy sources, except geothermal, are based on this proton chain, where protons in the sun are turned into helium-4. Basically, burning hydrogen as a fuel and producing helium are a dream for a very far future, imitating the sun, because we discovered as humans that reactions between deuterium and deuterium and between deuterium and tritium have a much faster lifetime. We can produce those reactions on Earth, whereas the reactions between hydrogen and hydrogen takes a long time, in the billions of years, in the stars in general. There is another fusion reaction that happens in different stars when you have temperatures above 200 million kelvins. We call this the carbon-nitrogen fusion chain. It is not the same as the carbon-nitrogen biological cycle. In that case, the main reactions, as we said, that some elements occur in the stars as catalysts. The catalyst in that case could be carbon. And the hydrogen in the star, again, at high temperatures, higher than the proton-proton chain reactions, combines with carbon-12 in the star as a catalyst. It produces nitrogen-13. Nitrogen-13 is radioactive. It turns into carbon-13, another isotope of carbon, plus a positron, plus a neutrino. That carbon-13 fuses with hydrogen, produces nitrogen-14. Nitrogen-14 fuses with Hydrogen again produces oxygen 15. Oxygen 15 decays into nitrogen 15 plus a positron, and then nitrogen 15 fuses with a hydrogen, producing carbon 12. And look here, carbon 12 and carbon 12 canceled out, nitrogen 13 and nitrogen 13 cancel out. They're all catalysts in that case. So in that case, the reaction is not the proton-proton chain or hydrogen plus hydrogen are interacting, but all these catalysts in the star combine to the production of 4 hydrogen nuclei fusing together and producing again our helium-4 in the star. So that happens at higher temperatures, above 200 million Kelvin, whereas the proton-proton chain that we discussed earlier. Let's look here. Oh, jump. That is only 220 million Kelvin. So you could see that depending on the size of the star and its gravitational energy, the nuclei are closer together and the reactions occur at different rates. In the carbon-nitrogen cycle, we have a problem with the internet, so we'll try to survive with it. The audio quality can be affected in that case if we have trouble with the internet, so please read the material in the lecture notes in general. With a branching of 1000, you find that the nitrogen 15 nucleus can interact in a different way. Nitrogen 15 in that case, and produces oxygen 16. Oxygen 16 produces fluorine 17, which returns back into oxygen 17. Again, this now we have now oxygen 16 and fluorine 17 as catalysts. If you cancel the catalysts from both sides, instead of 4 hydrogen nuclei, now it's 8 hydrogen nuclei, leading to 2 alpha particles or helium-4 nuclei. Another sub-branching is the oxygen 17 reaction can also interact differently with a proton. It becomes a much longer chain on both sides, but you could see all the catalysts there. So in fact, the reactions in those stars above 200 million Kelvin in temperature have not just hydrogen there interacting, but all those intermediate nuclei that have been formed initially from hydrogen fusing together in the nucleosynthesis process. That's called the process of nucleosynthesis. In that case, 8 hydrogen nuclei are producing also helium-4 with different numbers of electromagnetic radiation, gamma rays, neutrinos, and positrons. The positrons themselves would interact with negative electrons, producing 2 gamma photons, and neutrinos also are emitted. So here we are talking about in nature the fusion process of nucleosynthesis reactions, and the nucleosynthesis, meaning the production of nuclei in our star or the stars in the universe, are continuous, and learning about those nucleosynthesis reactions can help us understand how fusion can occur in a controlled fashion on Earth. Okay, so the first stage in stars, as we suggested, the brick that is used to build houses in that case is the protons, or the hydrogen nuclei. We showed here that in main sequence stars or other types of stars, you'll find that 4 or 8 hydrogen nuclei turn into helium-4. Now, what if the star has now been old and is depleted in the hydrogen? It has now helium primarily, so it turns into a different kind of star. You'll find that the core contracts to higher densities, and that is an implication that we'll learn about in terms of producing fusion energy also on Earth through what we are going to call inertial confinement fusion. And in that case, as the star gets older, it turns from what we call a main sequence star into a red giant. Our Earth, after in billions of years, will turn eventually into a red giant, it will expand, and that red giant will swallow the planets that are close to it, like Venus and eventually the Earth. But by then, humanity would have evolved to maybe expand into other star systems in general. We hope that will happen before the sun as a red giant will swallow the Earth when it expands in size. The highest densities and temperature in the core make now helium burning possible. So we find that other reactions happen, not just 4 hydrogen nuclei turning into helium. That helium that has been formed in the larger main sequence star or the red giant, you'll find these reactions occur at densities of 100 million Kelvin and very high density, 10 to the 5th grams of the plasma per centimeter cube. What happens to that in the red giants is that helium-4 now fuses with helium-4, producing beryllium-8. Beryllium-8 has a very short half-life, so it immediately interacts with another helium-4 nucleus and produces carbon-12. And if you add the 2 last reactions, you'll find that now 3 helium nuclei are turning into carbon-12 plus a gamma photon is emitted. Some additional helium can also proceed, fuse with carbon-12, produces oxygen-16. Okay, so now carbon is being formed. What if that star gets older? In a period of 10 million to 100 million years, most of the helium will be used up. The star now would contain primarily carbon, and that carbon now starts fusing together in the core. And these are 4 reactions where carbon nuclei can fuse together, producing magnesium-24, sodium-23, magnesium-23, neon-20. So notice here that process of nucleosynthesis that we are talking about. We started with hydrogen, turning it into helium. The helium can turn now into carbon. Carbon can start burning, and we have now magnesium, sodium, magnesium, and neon elements closer to the middle of the periodic table that are being formed at those older stars. Okay, at some point you'll find that carbon-12 and oxygen-16 now formed in those other reactions. Notice that the oxygen-16 could be formed in those earlier reactions here of helium burning. They start burning again. They combine and fuse together, and we get in the process of nucleosynthesis now elements like silicon-28. Silicon is very common in the universe. You find that sulfur-32 and phosphorus-32 is produced. And you could see here how the elements are being formed in those stars up to really the formation, as we'll see very soon. Silicon starts burning now. It produces, now in the middle of the periodic table, the nickel and the cobalt-56 and the iron-56. And these are the most stable nuclei in nature, iron and nickel. And we know that the outer core of the Earth and the core of the Earth are basically contain iron and nickel. So up to that stage, this comes from the burning of silicon-28. There are some other reactions that can also occur in this progression when we reach 1 billion kelvins. In that case, gamma photons can interact with the neon-20 and with sulfur-32, producing oxygen and 18. There are also other reactions other than gamma electromagnetic radiation interacting with the heavy nuclei, the alpha gamma reactions. These are alpha particles, the helium nuclei can combine with those heavy elements now, neon, magnesium, aluminum, sulfur, argon, and calcium, producing even calcium. And remember, calcium is part of our bones, and even titanium-24. But we did not exceed in all those reactions yet the nickel and the iron, which are the most stable elements in terms of the force, nuclear force that keeps the nuclei together. At temperatures higher than 1 billion Kelvin, you'll find that reactions with protons of all these other elements are produced, followed by positron decays. These are all reactions in the nucleosynthesis process in general. So you find isotopes of nitrogen, carbon, fluorine, and nitrogen being formed in those stars in general. Nucleosynthesis by exothermic fusion reactions can only proceed to the iron region. Iron, in terms of the energy, binding energy per nucleon, is and nickel are the highest in the middle of the periodic table. And a star that condensed out in its history of billions of years out of hydrogen cannot synthesize elements beyond the iron nickel region. Some part of it, like the technetium isotope, technetium 97, with 2.6 million year half-life, is detected in the spectra of some stars. There are variations, and basically that observations contradict the Big Bang theory advanced by G. Gamow, which postulates that element synthesis occurred by successive neutron captures in the first hour of the expanding universe. Okay, now how is it that we have uranium and thorium, whereas the process of nucleosynthesis here, as we suggest, can only lead to the production of nickel and iron? The best knowledge that we have about the process is now the process of supernovae. When a star ends up burning all its nuclear fuel, you'll find that the energy release is decreased. The energy release keeps the star in its geometry, its size, large size, and the gravitational energy now becomes larger than the energy that balances out with the energy, the expansion caused by the nuclear reactions. So at that stage, you find that gravitational energy takes over, and the star collapses upon itself, and we get the process of what we call supernovae. As again, the star collapses inwards, implodes upon itself, and in a supernova, there are two types of supernovae: type 2 supernovae, an exploding star, and type 2 supernovae, 1A supernovae. These result from all dead stars designated as white dwarfs. Now, why are we interested in these processes in the stars? Because, as I mentioned, we are interested in the process of charged particles interacting with the Earth's magnetic field in trying to trap those charged particles together in magnetic configurations similar to what happens in the Earth's magnetic field. But supernovae now, when a star explodes, the nuclei come so close to each other in the explosion that we form the heavier elements, the uranium and the thorium and all the heavy elements. And basically, supernovae are the process by which nucleosynthesis occurs beyond the nickel and iron in general. Supernovae is a model for another way of achieving fusion controlled reactions on Earth. And you could see that in that case, we name it as inertial confinement fusion. So in the process of the trapping of the charged particles around the Earth's magnetic field in nature, we can learn how to achieve fusion in a controlled manner using trapping of charged particles in the magnetic fields. That's the basis of devices that we call the Stellarator and the Tokamak and the tandem mirror that we are going to cover in the next chapters. But another process here is available to us where the explosion of a star. So can we get the nuclei to be fused together by imitating what happens in a supernova? And this is the basis of what we call inertial confinement fusion. And the supernovae are not pie in the sky. They have been observed as far back as in China in 1054, as well as Tycho Brahe in 1572, and the very famous Johannes Kepler in 1604. In 10,054, an astronomer in China, Yang, recorded observation of what we call the guest star that appeared for a day and lasted for a month. It was apparently a supernova explosion that created the Crab Nebula in the constellation of Taurus in the sky. Some people suggest that the Star of Bethlehem in the Bible story at the time of Jesus' birth could also have been a supernova explosion, or it may have been also a comet visit in general. Telescopes have observed supernovae. So you could see here, this is the remnant of the Cas A supernova that happened only about 22 years ago. You could see here after the supernova or the star collapses upon itself, implodes upon itself, a huge amount of energy is released, and pieces of the star now are spread around it into the cosmos or the universe. This is a picture of one of those supernovae that occurred, and these are the remnants of the supernova with a distance here of 12 light years. It takes 12 light years for the light to move from one side to the other of that supernova. An interesting aspect of life on Earth is that the Earth is suggested to be a remnant of one of these supernovae. Otherwise, we wouldn't have uranium and thorium and iron and nickel as in the core of our Earth. We are a solid, rocky planet. Whereas if you go to Jupiter, for instance, it's almost like a mini star. It's primarily hydrogen, or the farther the planet is from the sun, you find that it has no rocks. So it is assumed that all of us here on Earth and the Earth itself is a remnant, or those pieces of a supernova that happened 4.64 billion years ago, whereas we think that the age of the universe is 13.7 billion years ago, and that the sun, our star, the sun, grabbed some of those remnants for the inner planets, the Mars, the Earth, Venus, the inner planets in general. So in that case, we can detect those, or in fact, some backyard astronomers using some fun telescopes have been detecting them and reporting them and giving them the names that they think are appropriate for them. Supernovas are observed here. Let's see that diagram. This is called the light curve of Sn. Sn stands for supernova 1987A, and you'll find that it shows initially as a very tiny spot or dot in the star in the sky. You'll find that the luminosity the process occurs. You'll find that the luminosity increases about 80 days after an explosion. Then it decreases, but over a larger distance, and it can last over 260 days being observed in the sky. We see the luminosity light arriving to Earth first, then we see the X-rays, and then we see the gamma rays, and X-rays, of course, are moving at the speed of light in general. And these observations have been done by NASA with satellites, and this is another example of a supernova occurring. As I suggested there, our inspiration for achieving fusion using inertial confinement, where we try to imitate what happens in those supernovae. So you could see here another picture of a galaxy by NASA, the Swift science team, basically satellite there. And this is a satellite called the Swift Observatory in the galaxy NGC 277. You'll find here at the top an X-ray image of that galaxy. And at the bottom here, a visual or light image. And it shows here a supernova 2008. 2008 designates the year of that supernova. You'll find it also shows another supernova, 2007 UY. This shown here in the light spectrum. This one is shown here in the light spectrum. This is the galaxy NGC 2770, and you could see here that if you look in the X-ray spectrum, you could see how the X-rays are generated by that 2008, not too far in the past, and they seem to be common if you keep observing the sky. And this is another supernova that happened in 2014, only 8 years ago. November 6, 2014, this is the way it shows up. March 2015, you could see that the radius of the debris or the results of the explosion are moving out into the galaxy in that case, and they are spread all over the universe here. From November to October, took 2 years in observation. You could see the remnants of the explosion coming out. And this is what I've shown in the picture at the beginning of the lecture here. Let's go to all the way to the beginning. The supernovae here, that's a laboratory observation of a fusion device. Inspiration comes to us from the Earth's magnetic field in terms of confining charged particles to get them to fuse. And also another inspiration comes to us from the collapse of the supernovae in what we are going to call inertial confinement fusion, and we'll treat them in 2 separate chapters. All right, so we could see here why scientists study nature around us so that we can basically enhance our knowledge at the universe, obviously first, and second, maybe use it as a form of energy. And as Kardashev tells us, our civilization must try to reach the level 1 civilization on the Kardashev scale in general. Some of the, in the nuclear synthesis process, reactions, second generation star in particular, you find that carbon and helium can burn producing oxygen. Oxygen and helium can also burn producing neon. Oxygen and helium, oxygen 17. Let me see, that reaction is repeated here. And neon 21 and helium 4 gives us magnesium 24. Again, I insist that nuclear synthesis occurs up to the iron and nickel level. When we talk about uranium-238 formation, that is the process of supernova in general. The process of exploding stars or collapsing stars in supernovae is not the only process. Some people suggest that neutron stars, which are stars that have collapsed without causing a supernova, the neutron star becomes a very, very high density star. You'll find that those neutron stars can combine together, collapse and combine together, and that is suggested as another process of nucleosynthesis. Another process that can form the heavy elements is the process of gamma rays bursts. These are observed phenomena in the universe that can also lead to fusion reactions in general. All right, so let us look at then the fusion reactions, since we want to imitate them or mimic them on Earth to produce controlled fusion reaction. Obviously, it has to be what happens in nature that we try to imitate. The process of hydrogen and hydrogen producing deuterium reaction, releasing 1.4 million electron volt of energy, has a characteristic time of, look here, 100 followed by 369 years, 100 billion years. That is the time over which that reaction occurs. The deuteron fusing with a hydrogen producing helium-3 has a characteristic time of 1/2 of a second. Tritium fusing with a proton is 0.05 second. And obviously, we cannot really achieve that hydrogen-hydrogen reaction that happens in the stars on Earth as humans because of that very long characteristic time that it takes. Maybe we can get something in the range of the 0.5 second, 0.05 seconds. But in fact, we discovered as humans that some other reactions, like the DT reaction, has a characteristic producing an alpha particle and the neutron that imitates really the hydrogen plus hydrogen, but deuterium and tritium on Earth would have a characteristic time, that reaction called 0.0000012 second. So that reaction has a very short characteristic time of occurrence. And that's why it is used, in fact, in thermonuclear weapons or hydrogen weapons. Another reaction that is short in terms of the characteristic time is a DD reaction. The isotope of hydrogen deuterium fuses with deuterium. It has two branches. One branch we call the neutron branch, and one branch we call the proton branch. The neutron branch produces helium-3, and the proton branch produces tritium. And that tritium here confuses another deuteron, producing an alpha particle plus a neutron. There is another reaction where tritium and tritium can fuse together, producing an alpha particle and two neutrons. So this is a neutron producing reactions. So it seems that DT, having the shortest characteristic time, is going to be for humans the first reaction that is going to be used for a self-controlled fusion reactor. And deuterium plus deuterium would follow because it has somehow a longer characteristic time. It's more difficult to achieve. But notice that our oceans contain water, and 160 parts per million of the water is a deuterium isotope. We can extract that deuterium isotope and we can get out of it an unlimited amount of energy for our Earth to reach the level 1 characterization and on the Kardashev scale. So this is something in our future. It is a dream of the scientists in achieving an unlimited supply of energy, imitating on Earth what happens in our stars in general. Let us give you as an assignment to simply explore that carbon-carbon reaction and compare the Coulomb energy repulsion in fusion reaction. And again, this chapter as an introduction to plasma physics and fusion reactions is a way of gaining inspiration on how to achieve a self-sustained fusion reaction on Earth. I'll stop here. If there are any questions in the chat room, I'll be happy to answer them. Otherwise, we go to another chapter on fusion. I'd appreciate it is Alvaro can, oh my God, something happened here. Yeah, okay. Alvaro can take basically an attendance to get for people, encourage people to come in with a to the lecture rather than watching the video. And in that case, they get an extra credit point. All right, so there are, what is the chat room here? If I get any questions, I'll be happy to answer them before switching to another chapter. Okay, so let's go to sharing. Are we sharing now? I want to make sure we are sharing. The next chapter, if we consider fusion reactions, is, as I suggested, humanity's trying to imitate nature and trying to build devices where fusion can be occurring. And it is the really advanced challenge to science, because as I suggested, fusion is the main process by which energy is released in the universe. Fusion is the mother of all energies. You know that fusion occurs in our stars, the sun. Solar radiation comes to the earth. It's a basis of photosynthesis. It is also the basis of heating the ocean waters, producing wind, solar energy, and it is the basis of energy in the whole universe. This is a beautiful picture of the Cat Eye Nebula, NGC 6543 from NASA. You could see that the universe is basically a large plasma where fusion energy is produced. As I suggested, our view of producing fusion on Earth depends on using the isotopes of hydrogen rather than hydrogen itself, like what happens in the stars. Because of that characteristic time, the reaction occurs faster between those isotopes of hydrogen, the deuterium and the tritium, rather than the hydrogen nuclei itself. And as I suggested, these are the natural abundance of the different isotopes, the deuterium to hydrogen. If you take the reverse, it's at 160 parts per million that I mentioned. If you take the deuterium to hydrogen, is 1.4 10 to minus 4. So every 10,000 atoms of hydrogen, we have 1.5 atoms of deuterium. The same happens in the isotope of lithium. Lithium will become important to us in the same way in fusion energy, in the same way that it is important in the production of lithium-ion batteries for electrical vehicles. So it may become someday, if we achieve fusion, a resource problem, because the isotopes of lithium, lithium-6 and lithium-7, can interact with a neutron from a fusion reaction, in fact, and produce the isotope of tritium. And so we have interest in lithium as a resource for at least the first generation fusion reactions that depend on tritium, because tritium, as we'll see, has to be produced from lithium. Or we can totally bypass the D plus T reaction as a reaction for fusion and go from there directly to the DD reaction, where the isotope of hydrogen in seawater and rivers and lakes is used to produce future fusion reactions on Earth. Fusion is foreseen not just to produce electrical power, but also for producing fresh water from the salty water of our oceans, or brines also. Like brines are water that has a high concentration of salt that happens all over the Earth in very deep aquifers in general. We can use fusion to produce hydrogen. Hydrogen would be used in fuel cells to produce electricity today, replacing the approach of using batteries as lithium-ion batteries. As I suggested, lithium can become a resource problem in that case, so it can be bypassed by having the energy split the atoms of hydrogen and oxygen from water, and then hydrogen itself reversing the reaction of electrolysis, producing the hydrogen itself by recombining it with oxygen from the atmosphere in now what we call a fuel cell, getting electricity to drive motors for our transportation system in competition with the battery system for electrical cars. It can be used for the deactivation of fission reactor waste. It can produce also, as it produces neutrons, sources of fission fissile fuel from the non-fissile elements, like you can take uranium-238, absorb the neutron from fusion and produce fission fuel like plutonium-239 from uranium-238 for fission reactors, or you can use those neutrons, have them interact with thorium-232 and then use them in thorium type of reactors. And fusion used in space rocket propulsion would produce for us the highest level of specific impulse. So that would be the process of the impulse or the integral of force over time relative to the mass of the space vehicle, in that case, a rocket. And that high specific impulse means very high acceleration. It is our hope not just to reach a mission to Mars in a matter of weeks rather than years, but also our hope to reach the other neighboring stars for our grandchildren and children maybe. The progress towards fusion started during the Second World War. Some rumors exist about conventional explosive being unsuccessfully used by German scientists in attempts at producing the fusion of the nuclei of deuterium. Thermonuclear reactions had been looked for in gas discharges and exploding wires. So they got wires, they loaded them with the deuterium isotope, and then they ran a very high current in it. So the wire exploded, and the thought was that you create a plasma where the deuterons fuse together. These attempts were not successful, and Ernest Rutherford remarked in 1933, quote, "Anyone who looks for a source of power in the transformation of the atom is talking moonshine." However, another scientist, Hans Bethe from Germany, he described the fusion reactions in the stars in 1938, the ones that we just covered in the previous chapter, and he won the Nobel Prize in 1938 for that. The United States, after the Manhattan Project producing the fission weapons, was involved in what's called the Super Project, and that was the creation of thermonuclear reactions. It was opposed by Robert Oppenheimer, and Edward Teller went to the Air Force, and the Air Force started for him a laboratory, which is now the National Laboratory, the Berkeley in Livermore Laboratory in California in general. In the United States, an astrophysicist at Princeton University proposed and built a figure-of-8 type of a device that used magnetic confinements. He called it a Stellarator, and we'll study it in more detail, to be able to confine the particles of deuterium and tritium or deuterium in a configuration that imitates the Earth's magnetic field, where charged particles are confined in our Van Allen belt. At Los Alamos, a gentleman, James Stuck, started what he called the perhapsatron. That was an inductively driven toroidal system. And in 1952, a program were well established with other ideas, including mirrors. Tandem mirrors are evolving elsewhere. The Russians took part in the process since they were also developing thermonuclear weapons. Two scientists, Sakharov and Tam, suggested magnetic insulation in 1950. And Kurchatov, another Russian scientist, and also talked about it at Harwell in 1956. By 1958, the idea of thermonuclear fusion was not secret anymore for thermonuclear weapon, and was discussed in 1958 in a conference in Geneva. There were several Geneva conferences where the applications of nuclear energy in peaceful applications were discussed by scientists and created a momentum in this direction. An experiment called the Zeta experiment was built, and found that hopes are running high, and maybe some alternative concepts were considered in general. The inertial confinement concept that I suggested imitates the supernovae and the implosion of stars in general. This emerged from the American Weapons Stewardship Program, where nuclear weapon explosions in the atmosphere were banned, but the research continued in laboratories and computers. It's called the Weapons Stewardship Program. So in that case, weapons are studied and the processes in them are studied, but it has both the civilian as well as the military applications in general. In the United States, an invention by the Russians that the Russians named the Tokamak was also tried, and many European nations and Japan also tried the same configuration of what's called the Tokamak. So in that case, what we would like to do is study those processes. And right now, the research involves full participations of the European Union, the United States, Japan, and Russia on a very large tokamak. It's named the International Thermonuclear Experimental Reactor. Its abbreviation is ITER. It has been built and it's being put into operation in France at the center, I think it's Cadarache. Inertial confinement studies are continued by enthusiastic groups in Europe, the United States, and Japan, but large extrapolation on present technology of the driver. The driver is how to achieve the implosion using laser beams or heavy ion beams or electron beams. And the design of reactor systems are still very active because exploring the technical feasibility of an operational reactor that would achieve fusion for humanity in addition to fission, and who knows, maybe replacing fission in the long term, because it's basically an unlimited supply of energy depending on the water in our oceans. And we are a water planet. And if not water in our oceans, we can go to others like Jupiter, other planets, which is primarily hydrogen in that case. What's the advantage of fusion energy? Well, we have an abundant fuel supply. We discussed it, that it's being part of water in our oceans. It is a system that doesn't need a critical mass like what we studied in the case of fission. So in that case, the reaction would shut itself off if the conditions are not suitable for the reaction. Say you get a hole in the wall of the container of the plasma that is being fusion, the reaction shuts itself off. It doesn't need a critical design. It doesn't create air pollution. It doesn't create high-level nuclear waste like fission. And we can design fusion in such a way that it does not generate weapons material. Okay, so what are the reactions of interest? As I said, we cannot use the hydrogen reactions that happens in our stars. We know that in our stars, hydrogen would have a very long characteristic time, so that's out of the question. But the main reactions that we can consider is really using the isotope of hydrogen, deuterium. And deuterium plus deuterium, the heavy isotopes of hydrogen, have two branches occurring 50% of the time, producing a proton. We call this a proton branch. 50% of the time, the reaction produces a neutron. We call this the neutron branch. If you balance the DD reaction here that produces a proton, you get a triton, and that triton now can be available to fuse with deuterium. Deuterium plus tritium produces an alpha particle with a high energy neutron with 14.06. I wrote it as 14.1 million electron volt, and the total energy release is 17.6 million electron volt. We use that reaction when we studied Q values computations in general. The first, this reaction, of course, is used in thermonuclear weapon. It's the easiest to achieve with lower temperatures. So that reaction is considered the first reaction that would be used in future fusion reactors. But then because of the need to produce tritium from lithium, we may like to switch to the DD reaction. You notice here that the tritium produced from that reaction can immediately interact with a deuteron like here and produce that DT reaction if we are burning the deuterium. But deuterium plus deuterium needs a higher temperature than the DT reactions to be achieved in a workable fusion reactor. Also, that helium-3 from the DD reaction can immediately interact with a deuteron and produces an alpha particle plus a proton. And this reaction is very interesting because it produces only charged particles, whereas this reaction, some energy, both reactions occur really 50-50 all the time. You produce a neutron here, you produce a neutron here, and the lighter particle here takes most of the energy, 14 million electron volt, and here 2.45 million electron volt. But the deuterium plus helium-3 produces only charged particles, and charged particles can be used in with a magnetic field to produce basically a directed nozzle, and that reaction is a reaction that would be a candidate for a future propulsion system for space applications, because in that case you get the D plus helium-3, and the charged particles can be directed by a magnetic field in a nozzle to create thrust in a nuclear rocket. And that would be a rocket that would have a very, very high specific impulse characteristic of rockets. So let us think about a future where we are burning water. So in that case, we go to the oceans, we separate the deuterium through electrolysis from like what we have studied on how to produce heavy water. And we have deuterium in that case. So as we said, the deuterium fuses with the deuterium, produces a triton and a proton, the proton branch of the DD reaction. Or 50% of the time, you get a neutron branch and helium-3 is produced. Now, if your plasma is made out of deuterium, the tritium is produced here. It immediately fuses with deuterium and produces an alpha particle and a neutron. And if helium-3 is produced in the neutron branch, it immediately fuses with another deuteron and produces the alpha particle plus a proton. Each one of those reactions has a different Q value, but interestingly enough, if we add those four reactions, we get the same as what we mentioned in the previous chapter in those stars where we get some elements like carbon-14, for instance, acting as a catalyst in that case. So look here, you find that the triton and the triton cancel out, the helium-4 and the helium-3 and helium-3 cancel out, and you have here left 1, 2, 3, 4, 5, 6 deuterons. So the reaction says that we get 6 deuterons turning into 2 protons, 2 alpha particles, and 2 neutrons. Unlike really the 4 hydrogen that lead to helium-4, here 6 deuterons would produce 2 protons, 2 alpha particles, 2 neutrons. And if you add the Q values of all those reactions, you get 43.2 million electron volt. Notice that we have 6 here, 2, 2, and 2. If you divide that whole reaction by 2, then 3 deuterons would be producing about 21.5 million electron volts of energy. The reaction of deuterium plus helium-3 may need very high temperatures. So if it does not occur, then we name the reaction a different name. This is what's called the catalyzed Dd reaction. Remember that name because, of course, the tritium here is a catalyst. The helium-3 is a catalyst. If the deuterium plus helium-3 reaction at lower temperatures does not occur, we name that reaction the semi-catalyzed Dd reaction. So we eliminate that D plus helium-3 reaction. In that case, tritium is the only catalyst. 5 deuterons produce a proton, a helium-3 nucleus, an alpha particle, plus 2 neutrons in general. We know that deuterium occurs in the water in the oceans. It can be extracted through electrolysis or distillation. Tritium does not appreciably occur in nature since it is radioactive with a short half-life, 12.34 years. So you have to produce tritium or breed it from the isotopes of lithium-6 and lithium-7 by the interaction with the neutrons. Oh, here, look here, that reaction is producing 2 neutrons. And look here, that reaction is producing 2 neutrons. So those tritons can be used with lithium and producing the tritium as a product of the reaction itself. Here are the cross sections, as we'll call them. Remember, we described cross section for fission reactions. We also can describe the cross section. Now, in that case, the units are meter squared for the different reactions that we have described right now. The DT reaction, you could see, has a cross section of about 10 to the 3 or 4, 10 to the minus 28 meters squared cross section. The D helium-3 reaction has also the second in terms of the cross section. So this is a reaction that can occur with the highest probability at an energy of the plasma, not 0.228 million electron volt because of tunneling, though it can occur at 10 to 100 kilo electron volt of the energy of the charged particles in the plasma. The DD reaction, as you could see here, has 2 branches. It would have one order of magnitude or 2 orders of magnitude less cross section than the DT reaction, and that's why it's considered for second generation fusion reaction. This is the reaction, the neutron branch of the DD reaction cross section here. This is the cross section for the proton branch of the DD reaction. If you combine both of them, this is the curve that you get. If you separate the D helium-3 that we suggested would be suitable for propulsion, that is the curve for it. An interesting aspect of D helium-3 reaction is that the Apollo missions to the moon discovered that the dust or the regolith on the surface of the moon contains a significant proportion of helium-3. So some people have suggested that we should go to the moon, mine the helium-3 for the moon. Every year we can have a space shuttle bring in the helium-3 mine for the moon, and that D helium-3 reaction can supply humanity with all its needs in 1 year with a single space shuttle trip to load from the moon. So mining the moon for helium-3 to achieve the D helium-3 reaction is an interesting prospect in our long-term future. Now, the problem is that the DT reaction is the one that can proceed at very low energies, and we suggested that tritium has a short half-life, so it doesn't occur in the Earth's atmosphere. So, but we have lots of lithium, and we know that all of us right now are using some lithium-ion batteries. So if you get the neutrons from the fusion reactions that we listed earlier and let it interact with lithium as a metal surrounding the plasma where the fusion reactions occur, then a neutron it can interact with the isotope of lithium, lithium-6, produces an alpha particle E, and here we have the tritium. So we can isolate that tritium from the lithium and use it to drive the first generation reactor that would use the DT reaction. If the neutrons are fast neutrons that haven't been thermalized, the more abundant isotope of lithium, lithium-7s, would produce an alpha particle in neutron and another source of tritium. But it is an endothermic reaction. This is an exothermic reaction. So the energy loss here has to be taken into account, but of course we are producing an extra neutron. The DT reaction produces high energy neutrons that can turn or activate the structure of the reactor turn it radioactive, and a fast neutron from the fusion reaction can in principle produce 2 tritons in these 2 reactions. If you add the 2 of them, you can have 1 triton here and 1 triton here. However, I did mention that would pose us in the future a resource problem because lithium is used extensively now for the construction of batteries for electrical vehicles in general. So in essence, the easiest reaction to achieve is the DT reaction here shown in that table, where an alpha particle is produced and a neutron is produced. However, we have in that case, in addition to extracting deuterium from the water in the oceans, we have also to use the tritium. We have to use the neutrons from the reaction itself here, the neutron, to produce a tritium from lithium. So that would be the first generation reaction because it has the lowest the highest cross section of occurrence at the lowest energy of the ions. Second generation fusion reactor can use, of course, what I mentioned earlier, the catalyzed Dd reaction with its proton branch producing a proton here and its neutron branch producing a neutron right here. I suggested the TT reaction. I had a student work on a thesis on it. It's a reaction that produces lots of neutrons, here, 2 neutrons. But there are other reactions that can be considered in fusion, a whole list of them. For instance, we can have hydrogen, a proton, interact with lithium-6. So you can have a plasma in which you have hydrogen mixed with lithium-6 or with lithium-7. In that case, you get an alpha particle and helium-3, and you get 4 million electron volt of energy release. But it needs basically a much higher temperature than obviously the DD or the GT reaction. A proton can be also combined with boron 11. And in that case, you get a plasma that produces 8.68 million electron volt. And you can have a deuteron interact with a plasma containing a deuteron now, not proton, but deuteron with lithium-6 producing 22.4 million electron volts of energy. And that's the closest to what happens in the sun because it produces an alpha particle here. And with boron 11, you produce also an alpha particle. So we cannot really talk about the GT reaction here because of the non-existence of tritium on Earth without considering the 2 reactions to produce lithium, tritium from lithium, the fast neutrons with lithium-7 and the thermal neutrons with lithium-6. And we suggested that if we mine the surface of the moon for helium-3, we can produce a reaction on Earth producing an alpha particle plus 2 protons of energy. However, the progression of the engineering and scientific knowledge suggests that our first generation reactor using fusion in a controlled fashion would be DT reaction. We'll follow it with a DD reaction and then maybe explore the proton plus boron and protons with lithium-6 and lithium-7. Notice that they produce charged particles like the same as the D-helium-3 reactors. These are candidates for space propulsion and producing nuclear rockets in general. We can describe those reactions shown in the diagram in terms of empirical relationships, where a bond, of course, as we described it for fission system, is 10 to the minus 24 centimeter squared. And those reactions, when you combine the cross section and the average speed of the ions, this is called the sigma V type of a Maxwellian average cross section. You find them that they differ from DD to GT to D helium-3 to TT to T helium-3 reactions. And this is what is used in computations in general. A plasma is described by its power density in terms of that sigma V parameter. And for different reactions, we can get a power density or watts per centimeter cube. The next part of the chapter will be described in the next lecture, where we start talking about the fusion approaches, the inertial confinement fusion and the magnetic confinement fusion, by which we can achieve, hopefully, a controlled fusion reaction on Earth. And I'll stop at that point. I'll stop sharing. And if there are any questions in the chat room, I'll be happy to answer them. Otherwise, have a nice afternoon, everybody. I'm sorry, Anshal, I don't know what happened. Didn't let you didn't make you as a co-host, but I tried. So now you are a co-host.
Also, no, it wasn't from your side. I had some internet issues. That's why I got disconnected. You did make me co-host.
Oh, okay.
Yeah.
I did make you co-host, but somehow.
Yes, sir. Yes, sir.
Yeah.
You did make me, but somehow my internet got disconnected and I was.
I need you both as co-hosts
Yes,
because
sir.
last time